So guys, now let us discuss the use case of recursive mutexes. That is, in what situation would you going to use recursive mutexes, and in what situation the normal mutex would not work. So in big software projects, developers write functions independently. Every function is associated to some task. Alright. So let us suppose that some developer writes this function. The purpose of this function is to delete a given student record from this student database. And let us suppose that it is a multi-threaded software, and this student database is a shared data structures across threads. So ideally, the developer obviously would lock the student database mutex before performing any read or write operation on a student database. And then he will perform whatever operations he would like to perform on a student database. In this case, the developer is deleting the student record from this student database. And when the developer is done, obviously he would unlock the mutex. So I don't see any problem with this API. It is just perfect. Now let us suppose that after 3-4 months, some new developer joins the team and he happens to introduce a new API in the system. This API is remove failed student. And the purpose of this API is to walk this student database, find all those students whose aggregate is less than this aggregate limit, and delete all the students in this student database whose aggregate is less than this aggregate limit. Alright, so obviously the developer would again lock the student database mutex. Then he would access the student database, meaning he would simply walk on each record of the student database, compare the aggregate percentage of each student in the student database, and if the aggregate percentage is less than what was supplied as an argument, then he would simply reuse this API to delete a record from the student database. Alright, and when the developer is done, obviously he would unlock the student database mutex. Now note that the developer who wrote, let us call this API as API 1 and let us call this API as API 2. So the developer who wrote API 1 would not bother to see what is the internal implementation of the API 2. He would simply like to call the API number 2 because he knows that the API number 2 would make sure to delete the student record from this student database. Alright, so API number 2 would work as just like a black box to the developer who was writing the API 1. Alright, and this is what happens in the company when you write a code. You invoke already written APIs, and most of the time you only knows that what is the input to those APIs and what is the output of that API, without bothering what is the internal implementation of that API. Alright. So with this approach, now you can see that there is one problem. The problem simply is that when the thread T1 invokes this API, the mutex is locked here. And when the thread T1 invokes this API, the thread again locks the same mutex here. So same mutex is being locked again. It means that the thread T1 would undergo deadlock at this instruction. Alright, and the reason is simple. The same mutex is being locked again by the same thread. Now one would argue that the simple solution to this API is that you can write delete student record 2, that is a new API altogether. And the purpose of this API is simply to delete the student record from the student database, of course, but in this new version of the API, we were not going to log any student database lock or mutex. So let us see the implementation of this API. So you can see that this is the version 2 of the API delete student record. And in this API, we simply bother to delete a student record from the student database without locking any student database mutex. And remember, this API was introduced for only one reason, and that reason was that this API could be called from those APIs which lock the mutex already. Alright, so this is a valid solution. The only problem with this solution is that for each function, you would have to write a duplicate function The only difference is that in between these two functions is that one version of the function locks the mutexes, whereas the other version of the functions does the same operation but without locking or unlocking any mutexes. So this leads to code duplicacy. This is the valid solution, but with this solution comes the problem of lot of code duplicacy. You can always visualize that this function could be 500 lines of code function and could be complicated function, not as simple as you can see here. So now let us visualize the same scenario again, but instead of normal mutexes, let us assume that these mutexes are recursive mutexes. So if this mutex is a recursive mutex that is used in the program, then these two APIs are perfect, self-complete, and there is no bug whatsoever. All right. When the thread T1 invokes this API, the mutex is logged here. Let us call it locking number 1. And the same mutex is logged by the same thread here. All right. And obviously, as I said, that recursive mutexes must be unlocked as many times as it was logged by the same thread. The same recursive mutex is unlocked here, and the same recursive mutex is unlocked here as well. And since it is a recursive mutex, the thread T1 would not enter into deadlock situation at this instruction when the thread T1 started executing a program from this API, remove failed student. So recursive mutex simplifies things. In the scenarios where there is a possibility that the same API could be invoked from another API which locks the mutex already, then in those situations you must use recursive mutexes. So this was the case of recursive mutexes, and I hope with this example it is very crystal clear that why and where you should use recursive mutexes and in what scenarios the normal mutexes would fail.